solid foundation on concepts and terminologies that we'll be using. Then we'll move into building clusters using Raspberry Pis. Ordered them yesterday. They're on their way. Sweet. Okay. Packing them. So we've got 10 of those coming. We're going to be into 5 groups. Each group will be able to work with a couple of them. We'll build our clusters. And then the third part of it will be programming those. And in doing that, we're going to be using various resources. You're going to be building your own text, but you're going to build your text from other resources. So I'm going to show you what I'm pulling from, in part, as we go through these materials. So, and they're available on Blackboard, so you can certainly go out there, reference them, use them, print them out, put them in your books, whatever you might want to do. So let me show you those first. And then we're going to get started on the first of 4 foundations topics. And this first one's really just concepts and terminology is the very first one. Second will be pipelining, and then we'll get into hardware concepts and usually programming concepts. So those are kind of the 4 things that we're going to be focusing on. So these will be ones, I don't know why I stapled them. I think I had them. Copies. These will be ones you can put in your book. You can put it under a foundations type tab, so you have that. Now the idea of these you'll see is that you'll see these aren't completely filled in, but they will be when we go through them on the computer. So the idea is for you to put this in your notes, take notes, so you'll be filling in blank lines. We'll talk about them. As we talk about them, you'll want to add maybe some more notes beside it so that you have your own set of notes from me, but also your own independent notes that you can have. So you'll want that. But first, let me just show you out on Blackboard. Under Blackboard, I went to course materials. This is what's out there. So these, okay, I just see something I don't want to have. Turn it off. All right. So under course materials, these are basically the slides that I'm just going to be handing out. So this is the one, it's the student slides that I just gave to you. We'll do that for about 3 days. So we did it. Technically, we kind of started it on Wednesday. We'll do it today. We'll do it Monday. Then the next week we'll be doing pipelining. So I'll give you a new set of handouts for that for your book. And then a new set of ones for another week on parallel architectures, and then another one for the programming models. The reason I'm showing you this is if you lose yours, you get them all messed up, you don't like the way they wrote, you get messy, go ahead and print them out again, and you can refill things in for yourself. That's fine. Or if you wanted to make them nice and neat, you could download these. They're PowerPoints. You can fill it in and print them out so they're nice and neat. However you want, it's up to you. Just want you to know that they're available there. And then also under references here, these are the things that I'm using for those handouts. And so the first one is actually a website that comes from a Lawrence Livermore National Lab, and it's from an individual there. Basically, there's 8 tutorials. They actually have a workshop at this national lab, and this is really the tutorial that comes from the first of those, just overviewing supercomputing. And so it's just an introduction to parallel computing. So it's really a tutorial that's out there and available to you. And so you can see it there. You can actually obtain it. I think this is just linked to it. So if you want to, yeah, it's just a web link. You can actually go and get it. But that would be one of the key ones that I've used. Then there's a beginner's guide to high performance computing. That was just a paper that I found. It had some interesting information. It's a long paper, pretty thick, but it has some good stuff. This gets a little more detailed, a little more mathematically oriented in some of the things happening. But that's this one. Pipelining, when we get to that topic, that actually is this, which is a PDF. It's basically a chapter. Remember I said I used to offer a course in systems architecture, and there was a chapter in the book I used on pipelining. This is that. It's really old. It's like from 2002. but the concepts are the same, which is why I like this. So it's a good reference for you just to have if you want to know a little more about the underlying foundations and fundamentals of pipelining. But I pull a lot of information from this when we get to our pipelining topic, which is the next one. Okay? So that's that one. And then this Raspberry Pi Model 2, don't worry about that. In fact, I was going to delete that. I didn't. I'm just going to do it right now. You guys will help me edit my names. We're actually using a Model 3 here, so this is going to be useful. And then the other one, this, okay, I don't want you to download and print it because I purchased 5 copies of that for use in our lab. But I did the electronic copy, so they came in PDF, so I thought, well, I'll just make it available here. Right? But it's not meant for general use. It's meant for us to use in our lab. So we've got 5 valid purchases of it. If you want to purchase your own, you can. It was like $20, right? But I want it to be out there because we're going to use it in our labs, and I'll have printouts there. And if you'd want to just kind of look at it electronically and take a peek at some of the things. What it is basically this book. It's a Raspberry Pi supercluster. Okay, and this is the one we're going to use basically in the labs. And so there'll be one, I'll make a printout and I'll put it, you'll see eventually there'll be 5 lab stations back there for you with your Pis, and we'll build the clusters and we'll work there. And there'll be a book like, this book will be in each one of the stations, a printout of it. And in the book there's some nice chapters, real short and sweet, but it gives you some good information. The first chapter is just on clusters, parallel computing, and the Raspberry Pi, just the background. Chapter 2 is on setting up your Pi software and hardware. Some of ours is going to come already preloaded, so that'll be kind of nice. Then you get into parallel computing, which is MPI, which is a message passing interface. It's a type of parallelism that we can use. Chapter 4 is on Hadoop, which is a distributed application environment. Then we're going to do a MapReduce applications, Chapter 5, calculating Pis, Chapter 6. So we're going to work through those chapters. But it's available to you. It's going to be what we use in the lab. But again, I stress to you, don't print it off. Don't make a copy for yourself. Okay? I trust you all that you won't do that. But it is available there since we do have, I've just purchased 5 that we can use in class, and that'll be what we use in our labs. Okay? All right. So I just wanted to bring that to your attention. And then what we're going to do is now go to our start of our foundation. Of course, it'll say spring of 2016. That's when I put this all together. I just didn't bother to go and change the date. So we really are in 2018. For those of you wondering, it's just, this is when I created all of this 2 years ago. All right. Drew's here. Zach's working. Alex singing. Seth's here. Dan's here. Alice is here. All right. Let's go. So this is actually going to build, I know I was talking about the binomial architecture at the end of class on Wednesday. This actually has that in there. So we'll be kind of picking up right there. All right. So again, these are the sources that I've used for this. And you can see it's pretty much the same sources I just showed you online. This is that Liverpool lab, okay, or Livermore National Lab, cluster book, that chapter from the book that I have. There's another one on creating these Beowulf clusters. I use a little of that. I don't have a printout of it. I didn't put it out there. And then this was the actual full textbook that I used from that one. So anyhow, sources, I always think it's good and it's very important to identify where we report this information. Okay, so we were talking about the von Neumann architecture, so we're just going to pick it up right there. And so the thing about a von Neumann architecture is a basic architecture that most of today's computers are built from, except it basically was a single stream type of sequential architecture. So it doesn't do parallelism. But it's a great place to start because parallel architectures start from the non-parallel von Neumann architecture, and it adds components to make it parallel. And since this is what we talk about in our 252 class, which I know not all of you have taken, it's a good place to start here in just reviewing some of the key concepts. Because the idea of what we're looking at, remember those 3 questions we're looking at? Okay, where our the first one is where is parallelism found in modern day architectures? And then the next one looks at the types of architectures, and then the next one looks at how to program. So those are really the 3 questions. So this is really getting at that first question, where do we find parallelism? So the way we're going to start is, well, let's look at where we don't have parallelism and why. And so, this looks like it's right on the board here. So in the Von-Neumann architectures, we've said, what is this up here? Memory. So this is our RAM. Okay. And this down here is our CPU that we have. Okay. And what does RAM contain? One thing it contains is instructions. So up here we have instructions. So this might be instruction 1, instruction 2, instruction 3, instruction 1, instruction 2, instruction 3. What else does it have in there? And data. Okay. That's all memory has. That's all we're always working with. So you always want to remember that. We're talking about. We're always talking about instructions and data. I mean, that really makes up processing. Right? I have instructions that I want to execute. We need to execute them. And then we have data that is used by the instructions. So we have those 2 things, and they're both stored up here in our RAM. Okay. All right. So important to this whole concept, we've already talked about it on Wednesday, is the fetch execute cycle. Okay? Because we get into clock cycles, right, where we have clock steps. But the whole idea of the fetch execute cycle, once again in review, is what? Who can tell me that? Maybe someone that wasn't in 252, some of you other ones. Jacob or Taylor? What is that fetch execute cycle?
Input process.
It's an input-output process.
It involves that, but when I'm thinking fetch, what am I fetching? 02. What are we fetching?
Instructions.
Okay, so up here we have instructions. Okay, they have to be executed here, but they're stored here. So the whole idea is the computer, several million times a second, is doing nothing more than fetching an instruction from here, bringing it down into here so it can execute it. Then it gets another instruction from here, brings it down into here so it can execute it. Okay? You could translate this to a very real-world type problem that says, okay, relating to this would be if this was our memory here, right, and my office was the processor, and each of you had an instruction for me. Okay? First time through, on one point, Jake would have to go to my office, give me the instruction. That's fetching the instruction, right? Now he's actually making a copy of it, so technically we'd make a copy of Jacob, and the copy would go to my office, and I'd get the instruction, and he would still be in both places now. He'd be in memory, but he'd also be in my office. Pretty cool, okay, because we can copy that. Then when I'm done, then I'd execute whatever he told me to do, right? Then when that's done, then I'm going to come get the next one. So then Drew would have to make a copy of himself and go to my office and give me the instruction that he is, and then I can execute it. And that's just happening several million times a second in a computer system. We have our memory with the instructions. We have our processor. Processor needs to get those instructions one at a time, in this case because we're a sequential processor, into it. Okay? So that's all that the von Neumann architecture is really about. It's called the stored program model. The program is stored in a memory, which can have different instructions, so it can do different things, which is pretty cool. Right? Otherwise, you'd have one machine that can only do one thing. And it focuses on, you have an execution unit that really just executes the instructions, and you have a place to store the instructions. And the fetch execute model, again, several million times a second in our environment, is just getting an instruction from here, bringing it into the processor, executing it. Getting another instruction, bringing it to the processor, executing. Another instruction, processor, executing it. Okay? So really, at the highest level, just think about, we just have memory, instructions, and data, and then we have the CPU. Obviously, there are more parts in the CPU that we want to talk about here. Okay? And some of them we mentioned before. What were these arrows here? Go ahead, Dan. Yeah. Bus system. So they're just a set of wires, because if I want to get something from memory to there, I've got to have wires along which it can be transferred. There's no wireless inside a computer yet. It's all based on wires, and the wires are your bus system. So these are a set of bus system. This would be what we call the data bus. Because if I'm going to put data from here to here, I got to go this way, thus the down arrow. If I want to put data back into memory, I got to go that way, thus the up arrow. And so we have our two-way bidirectional data bus. Over here we have the address bus. So the whole idea is in memory, this is where we were referring to your student mailbox. You have an actual mailbox number. Well, that would be the address. And then you actually have what's inside your mailbox. That would be the contents. So when we're working with memory, we got to know what address are we working with, and then what's inside that address. And so this bus will tell the CPU can tell memory, here's the memory address I want. Here's your student box number I want. And then it can either put something in it, right, which is writing to memory, or it can take something out of it, which is reading from memory and bringing it back there. Okay? Just like you would your student box, you put something in it, you can take something out of it. And this bus is the control bus. Again, a set of wires. It does nothing more than says, am I going to read or am I going to write? So it's telling it what operation to perform, the control. It's controlling what operation, reading or writing. So if you think about it in memory, you just have to specify the address, what's at the address, and do we want to read or write from that address? That's what those buses are for. Okay? On this side, these things over here are all what we call registers. So all a register is it just stores information. It's just a temporary place to store information. Okay? So if in my office is the CPU, and you bring an instruction, I got to get some data, well, maybe I have a place on my desk where I can just put some of that data. That would be a register, because I can just temporarily store it there. Okay? So we have different registers. We have one called the MAR. Just think of it, again, it's address. Address the A, address the A, address the A. That's the memory address register. Okay? You can see it's connected, and it's not in here, but typically it's connected directly to the address bus. So when I put in here the address I want, it immediately goes on the bus and tells memory, hey, that's the address I want. So the point is the processor can tell memory what address it wants by simply putting an address in this register. That address will immediately be fed across the bus to memory, and that's how they communicate. Communication is always important between these components. How does your CPU and memory talk? Well, the bus is how they send information, and the CPU knows that if it puts that, the CPU doesn't know it, by the way, the engineer that created the CPU, right, knows that the way it's engineered is when I put something in the MAR, it's immediately on the bus, and I know that the memory uses that as the address it wants to access. Okay. Likewise, we have an MDR. That's the memory data register. Okay. And what the memory data register does is, well, we have the contents. So if I've got contents that I just read, I know it's going to be in the MDR. If I want to write something to memory, I know I have to put it in the MDR before I write to it. So that's just where we can temporarily store data that we want to work with. Okay. Or it could be instructions too. All right. So those are just a couple components. Another register I think we talked about last time is, as we said, we're just going to go through memory, fetch an instruction, bring it down, execute, fetch the next one, bring it down, execute. Well, the way I'm going to keep track of what instruction I want next is the address. So basically, I got to store somewhere the address of the next instruction I want. And that would be down here in the program counter. We call it PC. All the PC does is it stores an address that you're going to go get next. Okay? In programming terms, what's that called? An address. And you were working with an address. Pointer. Okay, so you're working with a pointer. Okay? And so that's what we're talking about here. So those of you that have had courses where we deal with pointers, that's all you're doing is storing basically a pointer to the next address of the next instruction. Okay. Once I read an instruction in, I've got to store it somewhere. So we also have a thing called the IR, which is the instruction register. Okay. All you're doing there is storing an instruction. Okay. Over here, these are just a number of what we've called the general purpose register. They're just going to be used when we need to temporarily store data. So that's all they're for, is just to temporarily store data. Okay? All right, so all that's right there, are registers. And they're just part of one thing that we study called that storage hierarchy, meaning RAM's part of the hierarchy. So we have CPU, we said, has its own memory. Then we have a thing called cache. And then we have a thing called RAM. And then under here we have our magnetic media, and we have our optical. So we have our optical drives and DVDs, and we have magnetic media. And now in here, they're kind of a little more fuzzy, are our solid state stuff. Right? But the idea is when we talk about, well, what do you mean by memory in a CPU? What are you storing there? Well, that's what these registers are. That's just memory up in the CPU where it can just store stuff. Okay? All right. So, continuing on the von Neumann architecture, okay? The two other components you can see they're highlighted here that are very important are right here. And the first one we'll look at is that thing called the ALU, arithmetic logic unit. Okay? So, arithmetic logic unit is what the ALU is. And that's actually, when we talk about fetching and executing, sometimes when you execute, you actually want to add numbers together, or you want to divide, or you want to compare is this greater than that. That's where this happens. Okay? So if when you're executing an instruction, it wants to do arithmetic or logic, which is arithmetic or logic, arithmetic being add, subtract, multiply, divide, logic being is it greater than, less than type logic, it does it here. Okay? So this really is at the heart of where a lot of the execution occurs, when it's mathematical execution. Okay? All right. And then this is the control unit. The CU. This is the unit that really is at the heart of the fetch-execute cycle, because this does this. It performs the fetch-execute cycle via a series of hardware control signals. Ooh, I forgot one thing too. This is important because that's our internal bus. So I can move things around inside the CPU, right? And you notice everything is connected to that internal bus. So I can be moving stuff around like that.
What was the IR? That's where the current instruction.
IR is the instruction register. When I read an instruction, when I fetch an instruction, I'm going to put it there. Because executing an instruction takes several clock cycles potentially. So I have to store it somewhere so I know what the instruction is I'm working with. And really, if we read through this, the IR usually is pretty much attached to the control unit. But for some reason, when we draw the line, then we leave it off to the side for a while. Okay.
So you can write notes.
All right. So the control unit, it performs that fetch execute cycle via a series of hardware signals. So something that's not shown on here, and I'm just going to put them all in. What happens is the control unit coming out of it, we don't see it, are a bunch of control signals. So for example, there's a wire, and this wire allows something to go from the MAR onto the bus. And then there's another wire. And if that wire is activated, it lets something go from the bus into the MAR. We call that the in and the out. And there's just all sorts of these wires. So every single one of these components is going to have wires coming here. Okay? So one of them's for in, one's for out. One's for in, one's for out. And that series of control signals really is saying at some time stamp, let's say at time 0. Let's say at time 0. If I want to move something, let's say from this program counter to the MAR, what two signals does this control unit have to send? Well, if it sends the PC out signal, which would be, and by saying the signal, I just mean that wire is 0, I'm just going to put a 1 on it, like give it a pulse of energy, right? Electricity. That puts whatever's in the PC, I'll just say it's X. That goes onto the bus. Because PC out puts whatever's here onto the bus. And then if I want it to go to the MAR, at the same time, I can do MAR in. And now I just transferred the contents of the PC into the MAR, because the out put it on the bus, the in took whatever's on the bus and put it in the MAR. And so by sending two control signals, okay, I'm starting basically what is the fetch process. That's what we mean by hardware control signals. It actually sends out, puts electrical current on a wire, and that wire will activate and cause things to either go in or out. Some of those, also those signals could be things like, because the ALU, remember I said it could add, subtract, multiply, divide, it could compare. Well, it has to tell it what to do. So there's an add signal, and there's a subtract signal, there's a multiply signal, there's a divide signal, right? There's a greater than signal, there's a less than signal. I mean, there's different signals that you can do. Okay? So it has, when you're engineering it, so if you're a hardware engineer and you're working at Intel, okay, one of the things you're doing is thinking through what are the hardware signals that are necessary to come out of this beast. Right? Then the other thing you're doing is, in order to fetch and execute then, here's the thing, the fetch, okay, you're going to have signals. We're not going to go through any other than this, but we're going to have signals. Well, a certain number of signals, they actually perform the fetch cycle. Right? So I might have it takes 3 time slices with 3 series of signals that actually would allow me to get the next instruction into the IR. Right? That's part of the fetch cycle. And then once it's in the IR, it's going to vary, but then there's going to be a given number of other signals, I'll just say n, that are necessary to actually perform the fetch, or excuse me, the execute. Okay. And then when the execute's done, it goes back and does the fetch again. So all that's happening millions of times per second is it's going through and sending out signals, sending out signals, sending out signals, which happen to make it fetch the next instruction from memory. And then it sends out a bunch of signals, sends out a bunch of signals, sends out a bunch of signals that execute whatever instruction we just got. When this instruction is done, it starts over. It goes, sends out a bunch of signals, sends out a bunch of signals, sends out a bunch of signals, it fetches the next instruction from memory. And then it executes that one. And it can vary depending on the one we fetch. Okay. That fundamentally is how a computer works. For those of you that didn't take 252, you just got a semester's worth of information in 10 minutes. All right. But you don't have to worry, I'm not going to, this isn't stuff I want you to memorize, but it's more the concepts. And the idea here is, notice everything is sequential, right? I can only work on one instruction at a time. That's key here. So right now, the only instruction I can work at is all of these steps right here. I was doing this sequentially, here, 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 in order to fetch and execute one instruction at a time. Right? Okay. And I had to wait. I couldn't start executing this instruction until I fetched it. So there's just a lot of single sequential processing happening here. You look like you have a question.
Well, you said that it has to like one instruction at a time, but it is pipelining.
Right, exactly. So pipelining will be our topic next week, which is one way to start making things happen in parallel. Okay, so the idea here is I just want to start with the basic von Neumann architecture that emerged back in the 40s and 50s, right? Because it was it still is a fundamental architecture upon which all computers are built. But its limitation was it was sequential. It wasn't parallel. It could only work on one instruction at a time. Okay. So all of these, what are these time slices? You know how people talk about clock speed on computers? Right? Computers can go so fast. Okay. Well, if you have a clock has cycles. Right? So you have clock cycle. That would be your hertz. Right? If you're in megahertz, you've got millions of these cycles per second. If you're at gigahertz speed, you've got billions of these per second. Or is it megahertz? Doesn't matter. Okay? The point is, each one of these is one of these time slices. So then you have another time slice. Okay? And then you have another time slice. So in this case, a single instruction took several clock cycles to finish because I was doing everything sequentially. Right? And so what we're trying to do is, while this works very well architecturally and it's what the von Neumann architecture provided us as a basis, performance-wise, it's very poor. Because I've got to just wait for one instruction to get done before I can start another. So the question is, where can we take this architecture and start introducing parallelism? When can we start doing more than one thing? But in order to do that, what would we have to do? We talked about this, but what were some of the things that if we want to do more than one thing at a time, what might we want to do? Now, you mentioned pipelining. Okay, that's the next topic. We'll get it next week. But what is pipelining? Just as a teaser. Okay, so as we said, what we're going to do is, let's say we take an instruction and we break this one up into the fetch part and the execute part. And let's say I rework that architecture so that I can be fetching one instruction while I'm executing a separate instruction. Now I'm overlapping just a bit the fetching of one with the overlap of the other, because now at this time 3, I could be executing one instruction, but I could also start fetching the next instruction. So now I can do 2 things at once, right? Which is pretty cool. And that's what pipelining really does. At this instruction level, it lets you overlap instructions inside this would be a core, by the way, inside a core. Okay? Right now, the way I have it set up, I can only do one instruction in the core at a time. Pipelining lets me overlap instructions in the core, depending on the number of stages, and we'll get into that next week. But what do I need then inside here? If I'm going to pipeline, what do I need to do? At least a couple things to this architecture.
More buses.
Yeah. So one thing is I only have a single bus. Okay. So if I'm going to be able to fetch an instruction and execute one, I've got to figure out how can I separate the bus into a fetch unit that has its own bus and an execution unit that has its bus. And oftentimes what you see is you have multiple buses inside here instead of one. That will allow us to do pipelining, which allows us to overlap. And now we have parallelism. Okay? So that's pipelining. So that's one way that we can improve this. Okay? But of course that might also mean other multiple buses. It might mean other registers. I mean, there's other things you might have to add to it. But that's one place to capture parallelism. What else could I do to improve and get some parallelism? I could add more cores. I could take this, boom, and I could make another one. Now what do I have? Okay, let's do 4 of them. What would I have if I have 4? I have a quad core. Right? That's pretty cool, because now each one is separate, right? Now think about this. If I have 4 cores, and each core can have multiple pipelining, right? So I could be working on, let's say I could work on 4 instructions with pipelining. Oh, we did the 2. So in one core, I can be working on 2 instructions at a time because I'm pipelining. Now I have a second core, I can be working on 2 instructions there. I have a third core, 2 there, a fourth core, 2 there. Now I have 8 instructions I can be working on at a time, okay? Because I have multiple cores, and each core can do multiple pipelines. And there's also a thing called threading, which allows you to do more per core also, okay? So that's cool, right? Where else could I do this? Where else could I add something now? So inside a core, I've added multiple stages so I can increase the number of instructions. On a single chip, right, I could have multiple cores, so that's cool. But what's the next level that I could do I could get more parallelism?
Multiple sockets.
I could add more chips, right? So now I'm getting into what's called a cluster. So I have a cluster that provides that, okay? And we have a picture that starts showing that. Okay, so let's work through here real quickly. Okay, so what this picture is showing, this is just showing how the von Neumann architecture works, right? You've got a problem, you break the problem into instructions, but what happens is your processor is the old von Neumann architecture. I can only work on that one instruction at a time, so I have to do this instruction first, then I can do this instruction second, then I can do this third. That's just sequential processing, okay? As we were talking, that's non-parallel, that's the von Neumann, okay? When we get into parallel computing, what the idea would be is I can take my problem and I can break it into parts, right? And each part can be working separately, right, that we have. And so that's what we're talking about here, is where we have parallel computing, okay? And what we want to identify with parallel computing is that first we can break the problem into those small discrete parts. And so that's what that's showing kind of over here. I can take my problem and I can break it into parts. Okay? And those parts, okay, they have to be able to be solved concurrently. Now what does that mean? Yeah.
At the same time.
Okay.
Without each other.
We don't get it.
Okay. So why would they? When couldn't I? I mean, why couldn't I always do it? At, you know.
If you were relying on the calculation of like the first part of the problem to solve the rest.
Okay. So think about, okay, all of you are mathematically inclined. So think about a mathematical problem, or maybe I'm calculating some variable here and I'm using that calculation here. Could I be doing these in parallel? Well, no, because I might start using the variable before I get it calculated. So they have a dependency on one another. So these two would not be able to be concurrent. Concurrency really talks about the structure. You have your problem broken down so that parts of your problem are actually concurrent, can be executed concurrently, okay? Which is different than parallelism, which really focuses more on actually executing them. So concurrency talks about, can I break the problem down into independent sections? And then parallelism, which is related to concurrency, is all about, now can I actually perform both at the same time? Can I actually do the executions? Right? So one's kind of more of creating the foundation and the architecture of it. The other is actually doing it in the same time. Okay? A good example of when you couldn't do something concurrently is when, yeah, there's a dependency on a variable that's calculated here that these might use. Right? This one would have to go first. If these three use that variable and they don't change it, well, I could do this one first, then I could do these three in parallel, right? Because they are concurrent. Those three are. But that's the difference between the two. Okay? And that's what we're talking about here, where it said the parts must be able to be solved concurrently and solved with a series of instructions. But then we can execute them simultaneously. That's the parallelism. So concurrency is really, can I solve them independently of one another, and then now I can execute them simultaneously, these instructions on different processors. One thing we always want to remember with computers, there's always overhead. When you are working on your Mac or you're working on your Dell or whatever, you have an operating system running, right? And that operating system takes clock cycles. This is a program, so it has software instructions that are fetched and executed. But that's a good thing usually, because if it wasn't, that means every program you would run has to manage its own memory and manage its own processor, and it would just be a real pain. Okay, and there'd be a lot of issues with that. So overhead's not a bad thing. It works on coordinating, okay, what's going on. Parallel architectures still need that also. They need that coordination. So you have to have some control coordination mechanism to coordinate that, right? Because you got it into pieces, but then how do you know when the pieces are done? Well, something has to be keeping track of, are you done, are you done, are you done, right? So it has to coordinate that. That coordination takes a little overhead. Okay? Your hope is that the overhead isn't so much that it takes out any performance benefits of doing it in parallel, right? That would be bad. And we've seen that in the past of some operating systems. They had so much overhead that they were just bringing your system down to its knees and you couldn't get any productive work done. But I just kind of a early tidbit on that because we'll talk more about coordination mechanism. Okay, so then, where's that picture? Oh, there's the picture. That's the picture I was going for. Still more about what is parallel computing. So again, the parallelism is the simultaneous execution of instructions. The concurrency is just more about the composition of the processes. Certainly related topics, right? They're related topics. There's actually a clip. I'm going to have you go look at it yourself since we're running a little low on time here. I'm going to have you go watch this clip. It's just a person from Google talking about what's the difference in concurrency and parallelism. But basically it's saying the same thing that's exactly up there. They're related. Parallelism is really trying to execute things at the same time. So when John said execute at the same time, you are talking about parallelism. If I'm talking about a problem that I can break into independent pieces that don't interact, now I can say they're concurrent. I can do those concurrently. But if I actually put them on a computer and start executing the instructions, now I'm doing it in parallel. So they're very closely related, but different concepts. And that's what he's getting at in this video. But I want to get to this one. Okay, because that's where we are. So when we talk about that first question, where is parallelism found in modern day computers? The answer is all over. Okay? And it starts with, here would be a cluster, right, of computers. So think of, this is a node which would be like someone's computer, PC. This could be another node that's like a PC. This could be a third node, fourth, fifth, sixth node. So these could be like 6 separate personal computers that are out there. They're just networked together. Okay? We're going to have one, you're going to be building one in here where you're going to have a Pi, and you're going to have a Pi. You're going to have 2 nodes networked together. Okay? And these Model 3s, John, what do they have multiple cores? I don't even know.
I don't know off the top of my head. I think so.
Are they single core? Okay. I just ordered them yesterday. I should have paid attention, shouldn't I? But I didn't. Okay? Let's just say they're dual core, right? They have two in them. The idea would be, and in these cases, they're quad cores, right? Okay, so there's at least 3 levels of parallelism going on here. The first level is, as we talked about, inside the core, we can do threads and pipelining. So we can have, inside a single core, we can have multiple instructions being worked on, right? Second level of parallelism is I could have multiple cores. So each of these cores could be doing their own instructions. So if I can be working on, let's say, 2 instructions in every core, well, here's 2, 4, 6, 8 instructions right there that I can be working on, right? Just inside one computer, right? That's called a node. That's in a cluster they call nodes. Okay? But now I have multiple nodes in my cluster. So just where I had 8, so I now have 8 times 6. So now I can be working on 48 instructions at one time in my cluster. I thought it was more than one, but that's okay. But yeah, so really this is a great picture of our Pi. If you just clop off these and you look here. The Raspberry Pis that we're going to use, even though they're small and they don't look like much, okay, they're going to have 4 cores, and they're going to be able to they're going to be running a Linux operating system that will allow for some pipelining and some multiple execution. So we're very much in this environment. Okay? But right away you're starting to see that, right? That you've got multiple layers of this parallelism. Now here's the key though. Software has to take advantage of it. If I have software that's written, and that software is written for a sequential machine, and I run that software here, it's only going to take advantage of a single core in a sequential way. So I'm wasting a lot of the processing power. So not only do you have to have the architecture where you have it set up that you can do parallel processing, you've got to make sure that you're using the tools in the software that take advantage of that parallel processing environment, or else you're just wasting that architecture. So in this class, we're going to be looking at all of this. So right now you're getting the foundations. You're going to look in and actually build a Pi that has a cluster with a cluster of 2 with 4 cores each, right? And then we're going to look at different software techniques that can take advantage of doing this. And that is going to be in doing some computational type work, okay, for those of you taking this from a computational science perspective. Because that's what you want. You're in here because you're going to be doing potentially some science, and you want to do some research, or you can do mathematics. And it has some heavy-duty computation, or it has some techniques where it's like, based on what I need, if I did this sequentially, it's going to take me hours, if not days, if not weeks. If I can get into a very supercomputing environment, high-performance computing environment, maybe high-throughput computing environment, I can really take advantage of that and narrow it down to an hour of calculation. And that's where the benefit's going to come in on that. Okay? So this is kind of really getting at the heart of that very first question. Where do you find parallelism in today's modern computer systems? And it's really inside the core, right, with pipelining and threads, multi-core machines, and then multi-node clusters. Right? You have at least 3 layers of parallelism going on. And there's still more, by the way, but that's just a nice way to think about it for this class, because there's other things happening in machines that are happening in parallel as we're moving along. Okay. All right. Okay. So that is kind of the what to the question. Then we get into the why. Why do we want to do parallel processing? So what would you think without, of course, you're already probably looking ahead. But what would you think? What are some of the benefits, obviously? The most obvious benefits?
Save time.
Yeah, I mean, you're improving performance, so you're saving some time on your calculations, right? It always gets back to the user. Right? The user has some application where they're crunching numbers or they're processing massive amounts of data, right? Big data, and they need better performing computers. Well, the way to get better performing computers is through parallelism. And so really that's getting into the why of this, okay? You're saving the time and money. Okay, that would be one. So given the same problem, because I can do it faster, I can actually maybe save time and money on that problem. Or you go the other way. Well, now I have larger problems that I want to solve, and parallelism will allow me to do the larger, more complex problems. Which, if you really think about the types of things that we're trying to, especially in like models and simulations, we're trying to model global warming, right? That's not a sequential thing, right? I mean, there's so many factors occurring when you try to incorporate the model that you got to set up in some type of parallel environment where you're doing the calculation. Certainly, we want to provide that concurrency so we can structure problems that if we can keep them separate in terms of concurrent, then we can do parallel processing. Okay. The last one we already talked about, making better use of underlying parallel hardware. This taking advantage of non-local resources, one of the things that I don't know if some of you have seen yet, and this would be a good topic for some of you, is there are, via the internet, very good high-performance machines available to you as researchers. You just get to them through the cloud. And so what you might do is research what are some of those that you can have access to, and how do you have access to them, what they expect of you, so you can kind of use some of that. Might be kind of an interesting topic to explore. Because then you don't have to build your own cluster, right? In this class, you're going to learn about parallelism. You're going to learn about building your cluster. You're going to learn about programming it to solve a problem. You know, you might cut to the chase and say, you know what, that's all interesting. I love the foundation. But if someone else can already provide me in the cloud a parallel environment and they give me instructions on how I can use it for the problem I'm trying to solve, I can bypass all of that. I don't have to build my own cluster. I'm just going to use one that's already out there. I don't have to program mine. I'm going to use tools that they already have available to me. Right? So you can cut to the chase on that too. And that would be a really good topic for some of you that are more interested in the application of parallelism versus the creation of parallelism. Others of you who are more interested in the creation of parallelism, yeah, you might want to look into, for your project, building a cluster other than the Pi, or you might want to be looking at different applications and actually program it yourself, those applications, just so you have some hands-on experience of working with some different tools other than just, you know, a small Raspberry Pi cluster. So you might want to take advantage of that. Okay. So as you're thinking about possibilities for the project, those are some options that you have. All right. And where do we use them? So we talked about what parallelism is. We talked a little about why we have it. Where do we have parallelism? It's all over. You know, this is just coming from that Livermore author. Just was identifying some of these high-performance computing areas. These are just the top 500. So somewhere they did a survey. I have no idea. But they just said, took a survey. What are the most, the top 500 areas for application areas? And you can just see they're all over, from aerospace, automotive, biology, consulting, defense, electronics, all the way through. Right? You can just see internet providers, retail. Okay. The world is not a sequential place. I guess that's the key. So when you're really trying to model problems you're trying to solve, if you try to model in a sequential environment, it's difficult. If you can apply parallelism to it and modeling, then you can start taking advantage of this. So again, that would be another area. If some of you want to find a particular, like, okay, I'm kind of into biology, where is parallelism used in biology? I mean, that would be a good topic for you to pursue when it comes to parallel processing. All right, on Monday, we're going to start here. Okay. So what we're going to see on Monday is that there's actually a taxonomy. And it's related back to the idea that in memory we have instructions and we have data, right? And so there are different taxonomies or ways to classify parallel architectures. This is one way. It's called Flynn's taxonomy. And it's a popular way. And it really is focusing on your instructions and how many streams you have. Do I have one set of instructions? Do I have multiple set of instructions? And your data. Do I just have one set of data I'm working on? Do I have multiple sets of data that I'm working on? And it basically identifies all four. So you can just see, here is my instructions. I can have a single instruction or multiple instruction. Here's my data. I can have single data, multiple data. Okay? And you'll see, and we're going to go over this a lot more, that the way this works, this was the old von Neumann machine, single instruction, single data. Multiple instruction, multiple data is most of our modern day computers now. Okay. The single instruction, multiple data, that's pretty much our GPUs, our graphic processors. And this one is pretty rare. Okay. It's not really used that much. It might be used in a few very specific environments. But we'll discuss this as we're going to pick it up on Monday. All right? Cool. Have a good weekend.